Okay, welcome to today's joint colloquium. I'm Wei Hao Wang from Academia Sinica, Institute of Astronomy and Astrophysics. It's my greatest pleasure to introduce our speaker today, Professor Wei Peng from CETA. Professor Peng got his college degree actually from this university, not the physics department, but the mathematics department. So he came to Taiwan as a foreign student. We call it Chaosen in 1985, I think, and studied in the mathematics department and got his degree in 1989. Then he went to the Electrophysics Institute of Jiao Tong University for his master degree. And after that, he went to Princeton University for Astrophysics, the PhD program there. Actually, I heard the story about how he got into Princeton. I don't know if I'm allowed to tell the story. You can ask him. But the story I'm allowed to tell is that when he just came to Taiwan, he couldn't read any Chinese, and he can only speak a little bit. But then he still managed to graduate from this university. It's quite an achievement. And after he got his PhD degree from Princeton in 1995, he went to Harvard as a postdoc. Is that right? Junior fellow, yes. And then now he's a professor at University of Toronto and in the Department of Astronomy and Astrophysics and Department of Physics. And he's also the Associate Director of CETA, which is a Canadian Institute for Theoretical Astrophysics. So Professor Peng is an expert on cosmology, theoretical astrophysics, working on various things in cosmology, 21-centimeter observations, and also pulsar. So today I believe he will tell us something about pulsar and quantum gravity. Please join me to welcome Professor Peng.
Should I be using this?
Yes.
Hello? Okay, thank you. Always an honor to be here. I was asked to try to give a talk that is accessible to a very broad audience, not just experts in astronomy or whatever, but everyone. So I tried. I don't know. I fear that maybe this is now understandable by nobody. So I need your help. And if things are not clear, please do ask, since I've never tried this before. So I will try to explain a bit of what I've been doing, what I've been thinking about, related to quantum gravity and how it may relate to effects that we may be able to measure now or in the near, hopefully not too far future. I want to start. I don't know how many of you have heard the news that it was this year that the first pulsar was found orbiting a black hole, in fact, the black hole in our galactic center. I think that is very interesting news and allows us to ask more questions of what such a system might do. Now, this system, I don't know whether it will be the right one. It probably is not the perfect system yet for studying the effect I will describe, but at least I think there should be a good motivation. It's something which actually happens in the sky, that you do get pulsars orbiting a black hole, and there's a lot. I think it's a very fascinating development. I'll give a very rudimentary review of the Hawking information problem of black holes. I give again a very short review also of a proposed solution to it called Fuzzballs. And then I will try to explain of how this kind of pulsar black hole binary could help resolve some fundamental questions of what a black hole is or is not. So quite an ambitious agenda to explain it. I only have 13 slides, including this one, so it's not a lot of slides, but I think it will be conceptually a bit of a lot of changing to be familiar with. Now, this is, as we just said, so this is an artist's conception about a pulsar, which is a neutron star that emits radio waves. In this case, it's a very special kind of neutron star called a magnetar, got a very strong magnetic field. For this purpose, none of that is important. What's important is that you have a radio source, like a radar, orbiting a black hole, and you can ask what you expect to see as it orbits. And what you want is, the important thing about pulsars is that they are very powerful lighthouses. They emit a lot of light. They're also sometimes used as clocks, but I will not be using the clock aspect of this pulsar. I'm just using the fact that a pulsar emits light and goes around a black hole. And there have been many papers, these guys were not the first, who have proposed that this is a great way of testing general relativity, because you now really have a clean object. With pulsars, the nice thing is you can measure things very precisely. You can measure things interferometrically. Whereas with optical light, it's usually very difficult to get phase-coherent phenomena. So just for the precision purpose, for radio measurements, there's nothing else I'm going to be using about what a pulsar is. And of course, there's a huge amount. People hold conferences on pulsars. The topic is very rich. Next ingredient. Why might this be interesting, or what has been the mystery about the nature of black holes? I think it starts with Hawking in '74. And Stephen Hawking realized that black holes radiate. Very amusing physical phenomenon. Generally, I think in the astronomy community, it thought to be not particularly relevant to any data. If you take, by the way, I've implicitly assumed for a typical solar mass black hole, and most black holes are probably more than a solar mass, a typical temperature, when you say radiate, it radiates as a kind of thermal emitter at about a microkelvin. It's the typical number you should have in mind. And you may notice that a microkelvin is colder than anything in our universe. And therefore, in fact, black holes don't radiate. They absorb microwave background photons from the microwave background. So this radiation is kind of a theoretical concept. This is what, if you had a black hole and nothing else in the universe, then it would radiate at a microkelvin. Not true for black holes in our universe. They really absorb things. But that's not important. The important thing is that this led to a thought experiment and a problem. Okay, what's the problem? The problem is that a microkelvin has the characteristic wavelengths, h over k, which is about a kilometer. Okay, so typically the way they radiate is a black body whose wavelength is comparable to their size. So what I'm saying is, if the black hole radius is roughly a kilometer, then it will emit radiation of a wavelength of about a kilometer. And of course, in astrophysics, this is not particularly interesting because this radiation would not make it through the interstellar medium. So you could not, it would be hard to observe this radiation from any black hole on our sky. But again, that's not important, as I said, because first of all, it's not radiating anyways. And second of all, it is this dilemma comes not because of anything in our universe. The dilemma comes, and this is why this is receives a lot of news, and I think this is probably some of the most popularly read about stories in physics as to this is causing a dilemma, and this is without any data even. Okay, this is a dilemma that is not related, so it seems, to any astrophysical measurement. And that's because Stephen Hawking realized, following on his discovery, that there's a problem. What's the problem? The problem is that there's something, this problem called information loss. Okay, and I'll go to that in the next slide. But let's just put a few numbers to this. The number of photons you emit, and again you can do this calculation very easily. You know the energy of each photon is kT. You know the mass of the black hole is mc squared, where m is the solar mass. Mc squared is, I don't know, 10 to the 55 ergs or something, some very large number. You divide it by microkelvin times Boltzmann constant, and you get about 10 to the 77, roughly, for a solar mass black hole. Meaning, and you emit about, for a black body of temperature K, you emit about a photon every wavelength. So it takes about 10 to the 77 photons for anything interesting to happen. Okay, for you to radiate away some half your mass, let's say. This is very slow. 10 to the 77, let's say milliseconds. That's how often they come out. That's a long time. Okay, 10 to the 77 is a really long time. It's a big number. But don't worry, we'll get even bigger numbers in just a few more slides. And let's just give you ideas as to what we're dealing with. We're dealing with something which hypothetically, for an isolated black hole, so we're many, many hypotheticals away from anything that's happening in our universe. But still, there's a big dilemma here, and let's see what the dilemma is. Okay. There's something called the radiation mechanism. You know, there are different ways of describing it. Personally, I like the description I think is the most physically intuitive, is something called the Schwinger mechanism. Okay. So, therefore, just to review how that works, is if I take a capacitor, just a normal parallel plate capacitor in a undergrad lab, and increase the voltage, then what we know, something interesting happens when the voltage reaches 2 times 511 kilovolts. Okay, at 1022 kilovolts. The potential is enough that you could create a pair of electrons and positrons in between the plates, and the electron will move to the positive plate and the positron to the negative plate, and of course the energy released by the electric charge separation is bigger than the rest mass of the pair, and that's called a Schwinger mechanism. And people are still trying to actually make that happen in the lab. It turns out it's hard to get the plates close enough not to get the whole thing to blow up on you. It's just technically challenging. People are working at it. There's a new laser system being built in Europe to actually create positron pairs out of thin air. I don't think anybody questions that this will happen when you just have a big enough electric field. So that's the Schwinger mechanism. It's inevitable whenever you have a strong field with enough energy that you can borrow energy out of the vacuum, out of quantum mechanical uncertainty, you will generate real particles, electron-positron pairs. Now, the analogy to electric charge and an electron-positron pair would be a gravitational field to a photon pair. Okay? So if I have just a gravitational field, then of course you can calculate, well, I can create a photon, and one goes up and one goes down, of a virtual pair, just like a positron pair, and going down, going up releases energy, and that's just a Schwinger mechanism. And in the case of a black hole, because I have infinite gravitational potential, I'm always ahead of the game creating these, and just a matter of how fast they get created. It's inevitable. Just need a strong field of any form. So whatever your field is, the thing that will get created is things that couple to your field. So if I had a slope, and I could create things rolling down the slope or the stairs, this is just very simple quantum mechanics and physics. Okay, there's nothing very deep about this thing, which is why people think it's very robust. Okay, it does not require many new understandings. It's a very basic result of quantum mechanics, and that's how you get all these numbers. So you generate one photon every light crossing time of the black hole. Now, the dilemma is that people think that black holes all look the same. Okay, again, you have to remember this. First of all, this mechanism doesn't actually. It's all a thought experiment so far, because we said real black holes don't really do this. But the dilemma is that black holes have no hair. So all black holes look the same, whether they formed out of a star or an anti-star or a strange star, doesn't matter. Once a black hole forms, after a few dynamical times, so certainly no more than an hour, all black holes will look identical except for mass and perhaps charge or angular momentum if you had that. Okay, there are at most 3 numbers that describe a black hole. So the black hole knows nothing about its formation history after you look at it, hours later, or milliseconds, a small black hole. Now, what we just said, the Schwinger mechanism is a mechanism that happens outside of the black hole. So the radiation that gets created cannot know about the inside. Okay, this calculation doesn't be calculated. It doesn't matter what happens inside. All that matters is that one photon goes in, the other one goes out, and it gets created out of a vacuum outside the black hole. So the photons coming out do not causally depend on how the black hole formed. Well, that's the problem. Why is it a problem? It's I suppose it depends a bit about what we think physics is, and not everybody agreed that this was a problem, or what kind of problem it is, but it does mean that there's a breakdown of, say, causality, or let's call this time reversibility. Okay, meaning I cannot predict the future from the past, or at least I cannot predict the past from the future, which I think is the same statement. Because we say, after a black hole evaporates and I collect all the photons coming out, well, those photons all came out of a vacuum. They came out of nowhere, and they contain no information about how the black hole formed. So at the end of the day, there's no black hole left. I'm left with a bunch of photons, 10 to the 77, a big number, but we're just doing a thought experiment, and those don't tell me what happened in the past of the universe. Okay, this is if you're a fundamentalist physicist, you will be very upset. If you're not, well, let's see what other problems you might have. So I think the story changed substantially. In fact, Hawking, I think, was one of the first to be willing to give up unitarity, and he says, well, maybe we're expecting too much of physics to say that it should be time that there is a fundamental equation that tells you the future from the past. It's all in principle, obviously. These are all in principle questions. Right? I don't think anybody claims he can predict the future or the past. But in principle, physics has broken down. But the story changed. So Hawking has made these famous bets, saying that he thinks that the universe is not causal. But Swimming and Raffa in '96, I think, changed the story. When they pointed out that, well, in string theory at least, you do get Hawking radiation, and it is time reversible. It is explicitly unitarity. It explicitly satisfies Schrödinger's equation, and this problem is gone away. Okay. So in '96, they can count the microstates of a black hole. Entropy is now accounted for, and everything is happy. Well,
Schrödinger Raffa did not, in their paper, did not state about the radiation part. They managed to reproduce a microscopic counting of entropy from the B1, B5 range. It's only after Modesina's CFT got this, a unitary conformal field theory deal with the black hole, then you have this unitarity result.
Okay,
it's slightly different.
Yeah, and understood.
But it's related around the same time there.
Yes, understood. This is a highly simplified history here of, and yes, there's much more that goes into the story, but certainly these are the first. But this is the point that actually matters for the subsequent argument of what happens in these black holes. And yes, I apologize for simplifying a lot of things as I go through these arguments. Now, if you now go back, and if I were Hawking, I would not have seeded this bet yet, because you still ask, well, but Hawking had such a good argument, okay? He says this information comes out of thin air, radiation really came out of nowhere. It really looks like, and this approximation is really good. I mean, you're so deep in the classical limit. How can it, how could this be wrong? Okay, so, and this counting, it turns out, actually is very hard to map onto Hawking's argument. The calculation is really simple. Everybody can reproduce it. You could give this as a problem set in in first year physics and quantum mechanics. Just take Schwinger mechanism and apply it here, and you will get the right weights. And what's wrong with this really simple argument? And it turns out it's fairly hard to map these stringy configurations onto a deep semi-classical limit black hole, and that's still not understood in detail. And there are different people who have different ways of trying to reconcile it. So I think this is a hint it's not a solution. So I'm going to go into a proposal by Samir Martha to this dilemma called a fuzzball. Okay, it's a proposal that that I personally I think appreciate a lot. Not everybody does, not even amongst the experts of that field. But it has some interesting views on what a black hole is about and what radiation is about, and I'll try to argue that this connects to what astrophysical measurements are about. So, Samir says, well, look, at the end of the day, something has to give, okay? So we have this simple calculation, we just said the Schwinger mechanism, just creating, pairs out of a vacuum. It can be electron-positron pairs, it can be photon pairs, it doesn't matter. And you sit far away, and, where did my history go? Where did the history of my universe go? Where's the information? Where's the cause and effect here? And he says, well, you really have to say something has to give. So what does Hawking assume? Hawking assumes that there is a space-time that is locally smooth and from which I can do a calculation. Okay, maybe that's wrong. He will argue that maybe the black hole horizon is not this nice and smooth thing, but rather a fuzzy fractal surface, in which case, maybe you're using the wrong background. This is probably, he's in the minority view. The more majority view, well, there are multiple views, but another solution is to make the quantum mechanics non-local. Okay, maybe those photons know about each other and about the history of the universe and other things in ways that we can't quite know how to describe. Okay, maybe an illusion that they only depend on things outside the black hole. Maybe they somehow do communicate to the, maybe there's that's non-local. A non-local approach is that the photons interact in ways that appear, either across the horizon or across to really far away from the black hole. These kinds of things would have to happen. Those are basically, and I think the non-local is currently more fashionable, but I'm going to describe what I think is a more interesting one, which is the Harry approach for black hole information. Okay, let's just do some basic estimates. I think in astrophysics, certainly people talk about the Saha equation, about thermodynamic equilibrium. So the probability of finding something in state n1, then to state, ground state, let's say, I'm going to call it n0, goes as the degeneracy of states times a Boltzmann factor, which is the energy difference, divided by the thermal temperature you're sitting in. Okay. So let's say I make this n0 a Schwarzschild black hole, and I make n1 whatever I'm going to actually measure this to be in. I want to ask, what could I measure a black hole to be like if I actually go and somehow make a measurement, whatever that means. Well, normally if I want it to be substantially non-Schwarzschild, okay, I want it to be not just different by some tiny amount, but no, I think I want it to be cubical instead of round. That's a major energy change. So you'd say, okay, to be interestingly different, we need mc squared of energy error in your measurement. And your temperature we just said is a microkelvin. This is some huge temperature. It's 10 to, well, I don't even know what that is. It's 10 to the, I guess 10 to 71 eV. Some ridiculous temperature, 10 to the Kelvin, some ridiculous energy. And then you divide those two, you get 10 to the 77. Okay. You take the negative sign of that, exponentiate it. Okay, that's a very small number. Okay, this is in fact the smallest number that I've ever seen in a calculation. This number is so much smaller than any, I used to work in cosmology where people were concerned about being off by 100 orders of magnitude between cosmological constants estimated and measured. That's nothing, okay, this is e to the 10, this has 10 to the 77 zeros. This is a truly, small number. Okay, this is so small, at this likelihood, everything is more likely than this, okay, just the thermodynamic probability of the whole of my atoms reconfiguring themselves and sitting over there is much larger than this happening. You would think, okay, this is the most unlikely thing you could even dream of. Okay, so you have to think hard to come up with something which is this unlikely. So even the most unlikely is more likely. So people normally say, well, forget this, there's no need to even think about the possibility of your black hole looking different. Samir points out, well, okay, you know, don't stop here. You've got one more term, and everybody should agree with that one. Degeneracy of states. That has to multiply it. So if your ground state for some reason was non-degenerate, has entropy has 1, then we know that the degeneracy, standard entropy formula, we've all seen the entropy of the black hole, that is 10 to the 77. That's just how many photons, entropy, that number of photons in a box. That's your entropy, very simple. 10 to the 77 photons are hidden inside. Okay, that's how the entropy comes about. By the way, this G, try this, right? You divide by KB, so this S over KB is equal to log, so you take e to the 10 to the 77 to get G1. Okay? That's the degeneracy, is e to the 10 to the 77. That's a big number. You thought you couldn't be more impressed by that just small number. Well, this is the biggest number you've ever heard of. In fact, it's so big, it cancels this ridiculously small number. Okay? So it was just an illusion to think that this is unlikely. In fact, you might be quite likely just by estimate. So if all you're going to do is estimate, how likely is it, you would conclude that this no-hair argument might have been off by 10 to the 77 orders of magnitude. Okay, that's a big amount to be, when we teach orders of magnitude, this is a big amount to be off by. Now, yes?
Yeah, what do you mean by non-Schwarzschild state?
By non-Schwarzschild, I mean, what I'm comparing to is in a textbook, it says that at zero temperature, okay, so when people say no hair, they implicitly mean that there's nothing to excite the black hole. So the universe is infinitely big and there's no excitations, and any perturbation you put on it damps, and then you get a Schwarzschild solution. And for certain perturbation, you can calculate that. They do damp down, and you do get some classically, at zero temperature, something which looks like a Schwarzschild black hole. That's what I'm going to call G0. G1, I want to say, okay, now I'm going to measure it. Okay, and I may get G0, I may get something else. And the probability of measuring something other than my Schwarzschild, let's say I want to measure a triangle instead of a sphere. Okay, what's the chance of that? Well, I've got to do this. And to be, when I say interesting, meaning very different, right? So that's why I'm going to put MC squared here. And of course, it's amusing that actually entropy, if it goes in area, a sphere has the minimum area, so it might be the least likely outcome. Okay, that's the basic order of magnitude thing. Okay, so maybe we're maybe this intuition that we have about black holes being round and Schwarzschild-like is misguided by 10 to the 77 orders of magnitude. Okay, we just we're not used to worrying about such big numbers. And Samir goes through and he shows that when you actually construct these things, obviously by counting microstates you construct one. Of course, if you actually know the true state of your system, then you have no entropy. Entropy is not knowing something. And of course, those solutions actually don't have a horizon, as you would expect. And the horizon really only comes about because you're averaging over states that you don't, you've got multiple states corresponding to the same energy, and that's where the horizon comes from. So one way of saying it is that whatever you mean by classical, the effective black hole we would like to describe as Schwarzschild, a superposition of these naked eigenstates that are just totally different. Okay, so obviously you get around Hawking's problem that you were just fooling yourself to think that there is a smooth background out of which photons get radiated. No, in fact, in the quantum mechanical picture, each of these eigenstates is nothing but like a smooth background. And if there were to be an analogy in his picture, if you want to see why you might get Hawking radiation from far away, it might be because you get transitions between these different microstates. Okay, and there's a very large number of them, and as you make a atomic transition between